Ah, Watson, the Great Pyramid.
And the Great Sphinx nearby, too. Oh, the mysteries of the East. I've always dreamed of visiting the land of the pharaohs.
Yes, but don't forget why we're here, Watson.
Oh, yes, the telegram from Moriarty to Sherlock Holmes, Esquire. All is forgiven, stop. Have discovered secret of your genius, stop. And here's the sealed envelope. What could this secret be, Holmes?
Moriarty has obviously discovered that I'm descended from the great pharaoh who is buried here. That's the only thing that would account for the brilliance of my brain.
So you really think that Moriarty wants to be friends now?
No question about it. He's finally realized it's quite impossible to outwit the mastermind. Shall we go in? Open sesame. I'm looking forward to meeting my great-great-great-great-granddaddy.
It's not his daddy they'll be meeting, but his mummy, or rather the greatest mummy of them all, Tutankhamen. When those bumbling detectives wake her up from her 6,000-year sleep, she will not be in a good mood. But just before the mummy makes mincemeat of them, I'll torment them by offering a way out if they can solve the riddle of the Sphinx, which I put in the sealed envelope, but which I know even the mighty Sherlock Holmes couldn't possibly figure out in time.
What the...
Open sesame.
Oh, I might have known it was a trap after all. That swine Moriarty has buried us alive.
Worse than that, I'm afraid, Watson.
Not the greatest mummy of them all, Tutankhamen. What on earth shall we do?
Open the sealed envelope.
The riddle of the Sphinx. If you can solve this mystery from this pyramid, you will escape scot-free. The great pharaoh had 3 sons, each 2 years older than the next. 4 times the youngest son's age, decreased by the middle son's age, was 12 more than twice the eldest son's age. How old were the 3 sons? But what does it mean, Holmes?
It means that if we know the ages of the 3 sons, we'll know which of these numbered stones to push to open the door and get us out of here.
But the mummy is almost upon us, Holmes. How could you possibly solve such a complicated riddle in time?
I've already solved it. The 3 sons were aged 22, 24, and 26. Close sesame.
We only just escaped a fate worse than death. But how in heaven's name did you manage to solve the riddle so quickly, Holmes?
Simple. Because we've come back to where we started.
What do you mean?
We've come to the mysterious East, where it all began.
Well, what all began?
Algebra, my dear Watson. Algebra.
Welcome to Program 10 in the Power of Algebra series. In the last program, we looked at algebraic fractions and saw that you deal with them in exactly the same way you deal with regular fractions. For example, if you have to add algebraic fractions with unlike denominators, you look for the least common denominator, in this case, 12x. Then multiply both parts in the first fraction by 4, and both parts in the second fraction by 3, to give us first this, then this. In this program, we're going to look at one of the fundamental skills that underlies doing almost anything in algebra, translating word problems into algebraic expressions, going from words into symbols. Algebra is a language of symbols, a bit like the abstract designs on these oriental carpets. Only algebraic symbols are actually very simple. Some of the most important ones are the signs for the 4 basic operations: addition, subtraction, multiplication, and division. Each of these signs is a single, unambiguous way of saying what can be expressed in a variety of different, sometimes not very clear, ways in ordinary language. For example, when we talk about addition, we can say the sum of x and y, or x and y are added, or x is increased by y, or y more than x, but algebra simplifies all these expressions to x plus y. In the same way, when we're dealing with subtraction, we can talk about the difference between x and y, or y subtracted from x, or x decreased or diminished or reduced by y, or y less than x, but in algebra, it's simply x minus y. In multiplication, we can say the product of x and y, or x times y, or x and y are multiplied, but in algebra, it all boils down to xy. Finally, in division, we can say x is to be divided by y, or y into x, but algebra writes it x over y. When you combine several of our awkward ways of talking about operations in word problems, things get even more complicated. Look at this example. Twice x decreased by 3 times the product of y increased by z in the difference between 3a and 4b. Well, all that means is 2x minus 3 multiplied by y plus z multiplied by 3a minus 4b. Formulas are another good example of how good algebra is at simplifying things. Instead of saying to find out the area of a rectangle, we take its length and its width and multiply them together. Algebra says A equals LW. Or instead of saying to find out the distance you're traveling, you multiply the rate at which you're traveling by the rate you're taking time to travel. Algebra says D equals RT. Okay, so the language of algebra is actually one of the clearest and simplest languages of all. That's not the problem. The tough part is to see through the tangled screen of ordinary language that obscures the crystal clear algebraic truths that lie behind it in your average word problem. Is that a little too lofty for you? Okay, we'll look at some questions you can ask to help to translate word problems into simple algebraic equations. 1. What do we need to know? In other words, what are the unknown variables? 2. What do we know already? 3. Can we draw a picture to help us see the relationship of what we know to what we don't know? And 4, how do we put all this into an equation? Let's start with a simple problem, this rug. Now, I have no way to measure it. All I know is that its length is 1 meter more than its width, and that it takes 14 meters of fringe to go around it. So, what are the measurements of this rug? To translate that problem into algebra, start with the first question. What are the unknowns? The measurements, the length and the width. Do we need variables for both? No. Since the length is 1 meter more than the width, we actually only need a variable for the width. So let W stand for the width. Second question, what do we know already? Well, as I said, we know that the length is 1 meter more than the width. In algebraic language, length equals W plus 1. What else do we know? That it takes 14 meters of fringe to go around the rug. In other words, that the perimeter of the rug is 14 meters. Do we know anything else? Yes. We know the formula for the perimeter of a rectangle. P equals 2L plus 2W. Now, to help see how these things all relate to each other, we come to the third question. Can we draw a picture? Sure. We can make a sketch of the rug. And then label the sides of the rug. The width is W, and the length is W plus 1. Now it's clear that the perimeter of the rug is all of these variables added together, which gives us the answer to the next question. How do we put all this into an equation? Answer: by taking the perimeter formula and substituting our variables. P is 14. 2L is 2 times W plus 1, and 2W remains 2W. Let's reverse this to get the variables on the left. Now we can solve it. To discover that the width of the rug is 3 meters. Therefore, the length, which is 1 meter more, is 4 meters. So, the rug measures 3 by 4. That was an easy problem, but the same process of asking basic questions applies to much more complicated-looking word problems, like this one. Jack and Jill leave the same point driving in opposite directions. Jack averages 10 kilometers per hour more than Jill. After 2 hours, they're 308 kilometers apart. Find the rate of each. It looks tricky, but it isn't. First question, what are the unknowns? Jack's rate and Jill's rate. Well, if Jill's rate is x, and Jack's rate is 10 kilometers more than that, then Jack's rate is x plus 10. Second question, what do we know already? Well, we know that the time involved is 2 hours, and the distance 308 kilometers. So t equals 2, and d equals 308. Do we know anything else? Yeah. We know the distance rate time formula. D equals RT. Now what looked like a complicated word problem has been simplified to this. Just like before, to help see the relationship of these things, ask that third question. Can we draw a picture? Yes. As a matter of fact, we can draw 2 pictures, a chart and a sketch. First, a chart with the formula at the top, and Jill and Jack at the side. Then we fill in the blanks. Jill's rate is x. Jack's rate is x plus 10. The time in both cases is 2, and since distance equals rate multiplied by time, the distance in Jill's case is 2x, and in Jack's case, 2 times x plus 10. We can also draw a sketch to help us see how everything fits together. We know that the total distance is 308 kilometers. We also know that Jack and Jill leave the same point, driving in opposite directions, with Jill's distance being 2x and Jack's distance 2 times x plus 10. Now it's easy to see what the answer should be to our fourth question. How do we put this all into an equation? Because the chart and the sketch make it clear that the equation is simply that Jill's distance plus Jack's distance equals the total distance, which is a cinch to solve. Telling us that Jill's rate is 72 kilometers per hour, and Jack's, which is 10 more than that, is 82 kilometers per hour. If only Moriarty had known about this simple technique for solving word problems, he might have realized that his riddle of the Sphinx wasn't so difficult after all.
But I say, Holmes, what has algebra got to do with solving riddles?
Everything, my dear Watson. Most algebra problems come in the form of word problems, and word problems are riddles after all.
Why are you drawing question marks in the sand, Holmes? Oh, yes, of course, the questions we can ask to solve word problems in algebra.
Oh, first class, Watson. So, to our first question, what are the unknown variables?
Well, the ages of the 3 sons. Shall we call them X, Y, and Z?
Oh, no need for all that, Watson. We only need one basic variable here, since we know that each son was 2 years older than the next.
Oh, I see. So if the youngest son's age is X, the middle son's age is X plus 2, and the eldest son's age is X plus 2 plus 2, or X plus 4.
Quite so, which brings us to our second question. What do we know already?
Well, we know that 4 times the youngest son's age, that's 4x, decreased by the middle son's age, which we write in algebra as minus x plus 2, was 12 more than twice the eldest son's age, which becomes equals 12 plus 2 multiplied by x plus 4.
Why, that gives us our equation already. Yes. So we can skip both the third question, can we draw a picture, and the fourth question, how do we put this into an equation?
Because our word problem is already in the form of an equation. First we get this, then this, which we can rearrange to this, which gives us our answer, x equals 22. So the youngest son's age was 22, the middle son's age was 2 more than that, 24, and the eldest son's age was 2 more than that, 26.
If that incompetent thinks he can fool me with a silly riddle, he's got another think coming.
Famous last words, because I have got another Sphinx coming, and another, and another.
Help!